Assalamualaikum warahmatullahi wabarakatuh. Today, I want to present for subject BRT 3373 Digital Signal Processing, and our title is Rectangular Window and Hann Window. And I want to introduce our lecturer is Miss Isadora binti Mustafa. And next, I want to introduce my team members. My name is Muhammad Alif bin Zakaria, B122410530, and my partner is Muhammad SHAHRUL bin KAMARUDIN, B122410464, and we are from class 2 BERT AS1/1. In our presentation, we have three objectives. The first one is demonstrate and the characteristic and difference of different filter. The second one is organize technical content. And the third one is explanation of the chosen windowing filter and explanation the application of the filter, like in the rubric objective. First of all, for introduction, for interacting with the window and Hann window. Two fundamental window functions in signal processing, particularly when utilizing the Fourier transform to analyze signals, are the rectangular window and Hann window. The most basic type of window is the rectangular window. Every sample in the signal is given the same weight. As a result, it offers high frequency resolution, but it also results in high spectral leakage, which may cause undesirable frequency to show up in the analysis. In contrast, the Hann window smoothly lower the signal value of the start and finish. The result in a cleaner frequency spectrum and less spectral leakage. In contrast to the rectangular window, its frequency resolution is marginally lower. And then I go to objective, like in the rubric that we want to achieve in the group presentation. The first objective is to understand and apply windowing technique in the design of FIR filter, which allow the development of filters with low pass, high pass, and band pass filter frequency response characteristic. Next is observe how the windowing function affect the output signal after applying the design FIR filter to an original. Next is to evaluate and compare filter made by rectangular window and Hann window in terms of their frequency response properties, main lobe waves, side lobe, attenuation, and roll-off rate. Next, we go to comparison between rectangular window and Hann window. First of all, we open MATLAB and at the command window, we type window and enter to to in to open the window designer. Okay, the first window type, you can choose rectangular, and the length you can put 21 as I want, and then you apply. As you can see, the time domain graph in the left side show the window amplitude versus the number of sample. This is the y-axis amplitude, and the x-axis is sample. Okay, we can see the amplitude is constant, equal to 1 for all sample. This means the rectangular window does not modify the signal shape in time. It simply keeps all sample with equal to weight. Next, the right side is frequency domain. The frequency domain plot show the magnitude response in decibel versus normalized frequency. The main lobe, this is the main lobe, is narrow, which means the rectangular window has good frequency resolution. Then overall, the rectangular window is simple and preserve the signal in the time domain, but in the frequency domain, it produces high side lobe and more spectral leakage. Next, we go to the second one is Hann window. We click at the new window for the window 2, and then type, you choose Hann, and then the length you can type 21, as you can see in the rectangular window. Yeah, as you can see, the left side is a time domain graph. The Hann window has a smooth and bell shape curve for time domain. The y-axis is amplitude and the x-axis is sample. This amplitude start from 0, gradually increase to a maximum value 1 to the center, and this smoothly decrease back to 0, and then smooth transition reduce sharp discontinuous at the window edge compared to the rectangular window. Okay, for the right side is frequency domain graph. For y-axis is magnitude and the x-axis is normalized frequency. Okay, untuk for frequency domain graph, plot show in the magnitude response indivisible versus normalized frequency. Compare the rectangular window, the main lobe is wider, which means the frequency resolution is slightly reduced. However, the slight lobe are much lower with slight lobe attenuation of negative 300 for magnitude in dB. Overall, the Hann window provide a good balance between frequency resolution and leakage reduction. It sacrifice some resolution by having a wider main lobe but achieve much better side lobe attenuation. Next, we go to demonstrate the window for rectangular window. We have which is three pass filter. The first one is low pass filter, the second one is high pass filter, and the third one is band pass filter. We need to put the input in the MATLAB coding for rectangular window. Fs equal to 1000 for sampling frequency, Fc equal to 150 for cut off frequency, and N equal to 21 for filter length out of symmetry. Okay, when we run, and then this is the output of low pass filter, and for low pass filter is the graph magnitude response of the filter. The x-axis, this one, the x-axis is frequency, and the y-axis is magnitude indivisible. At low frequency, the magnitude is high, which means the signal allow the pass around 200 Hz. The magnitude drop sharply. This is the cut off frequency. After the point, the magnitude become very low, meaning the high frequency signal are reduced or removed. Overall, the graph show the filter pass low pass filter frequency and block high frequency, so it is a low pass filter. Next, we go to MATLAB, and then we go to next part is high pass filter. So for the high pass filter, we just change at convert low pass to high pass filter in this input coding, and then when we run, the output for magnetic response will come out with the x-axis is frequency and the y-axis is magnitude. At low frequency, as you can see, at the low frequency, the magnitude is very low, which means the signal attenuated or blocked around 300 or 350 Hz. The magnitude increase sharply. This is the cut-off frequency. But this one is the high pass filter. The higher frequency, the magnitude is above 0 dB, mean the signal is allowed to pass. Therefore, the filter blocks low frequency signal and high pass frequency signal. So it is a high pass frequency signal. Next, we go to next band pass filter coding in the MATLAB. As you can see, for band pass filter, we input Fs equal to 1000 for sampling frequency, F pass 1 equal to 100 for lower cut off frequency, for F pass 2 equal to 300 for upper cut off frequency, and order equal to 220 filter order. And then you can put this coding. You can put this coding, design the FIR filter with rectangular window. which is a band pass. And then if you run, and then the figure 3, okay, you can see the figure 3, the magnetic response. So the magnetic response, as you can see, this graph show the magnetic response of the filter. The x-axis is normalized frequency, and the y-axis is magnetic indivisible magnitude in dB lah. So in the medium frequency range, this one, the medium frequency range, the magnetic is close to 0 dB, which means the signal is allowed to pass. At low frequency and high frequency, the magnitude is very low, so those signals are blocked. This means the filter pass only a certain range of frequency and reject the rest. Therefore, this is a band pass filter. I want to compare from low pass filter graph and high pass filter graph and band pass filter. As you can see, the three graphs show the magnetic response of different type of filter, which describe how each filter affects signal at different frequency. The first graph, low pass filter. In the graph, low frequency signal are allowed to pass with the little or no attenuation, while high frequency signal are strongly reduced after the cut-off frequency. The second one is the high pass filter. The low frequency signal are attenuated, and once the frequency pass the cut-off point, high frequency signal are allowed to pass. The filter is useful when low frequency component or interface need to be removed. Next, we go to band pass filter. The third graph, as you can see in the window, this third graph for magnetic response is a band pass filter. In this case, only a specific range of medium frequency is allowed. Range of medium frequency allow to pass, while both low and high frequency are attenuated. This type of filter is often used when only a certain frequency band is needed. In comparison, low, high and band pass different between a graph frequency range. The low pass filter passes low frequency. The high pass filter passes high frequency, and the band pass filter passes only a selected range of frequency. Now we move to next presenter, SHAHRUL to explain about Hann window.
Now I will explain about low pass filter used in this MATLAB code. A low pass filter is a digital filter that allows low frequency signal to pass through, while the reducing high frequency component such as noise. Low pass filters are commonly used in audio processing, biomedical signal like ECG and communication system. In this code, the sampling frequency set to 100 Hz. This means the signal is sampled 1000 times per second. The cut-off frequency is 150 Hz. So frequency below 150 Hz are allowed to pass, while the frequency above this value is attenuated. The filter rate is chosen as 51, which is the odd numbers to ensure a symmetric impulse response and linear phase behavior. Next, a Hann window is applied. The Hann window is used to smooth the edge of the impulse response. This helps reduce spectral leak and produce a smooth frequency response compared to a rectangular windows. The ideal low pass filter is generated using the sin function. However, since the ideal filter is high infinitely is multiplied by the Hann windows to obtain practical and reusable FIR filter. The input response plot show a metric waveform, which indicate that the filter has linear phase and stable behavior. The frequency response plot show that low frequency component below 150 Hz are passed with the minimal attenuation. With the minimal attenuation, while the higher frequency are significantly reduced. This confirms that the filter works as a low pass filter. In conclusion, This low-pass filter design use the Hann windows effectively reduce high-frequency noise while the preventing important low-frequency signal. It suitable for real-world digital signal processing application. Now, I will explain the high-pass filter used in this MATLAB code. A high-pass filter is a digital filter that allows high-frequency signal to pass through, while the attenuating low-frequency component such as slow variation and baseline noise. High-pass filters are commonly used in audio processing, biomedical, signal, and communication systems to remove unwanted low-frequency interference. In this code, the sampling frequency is set to 100 Hz, which means the signal is sampled 1000 times per second. The cut-off frequency is 150 Hz. The frequency above 150 Hz are allowed to pass, while the frequency below this value are reduced. The filter rate is chosen as 51, which is the odd numbers to ensure a symmetric impulse response and linear phase behavior. A Hann window is applied to smooth the edge of the impulse response. This helps reduce spectral leaking and produce a cleaner frequency response compared to a rectangular windows. The high-pass filter is created using this spectral inverse method. The high-pass filter is created using the spectral inversion method. This is done by subtracting the ideal low-pass filter response from a unique impulse, resulting in a filter that blocks the low frequency and pass high-pass filter. The impulse response plot showed a symmetric waveform, indicating that the filter has linear phase and stable performance. The frequency response plot showed that low frequency components are higher attenuated, while the highest frequency pass through with the minimal attenuation. This confirms that the filter operates correctly as a high-pass filter. In conclusion, the high-pass filter design using the Hann windows effectively removes low-frequency noise while presenting high-frequency information, making it suitable for practical digital signal processing application. Next, I will explain the bandpass filter implement using Hann window with a noise audio signal. This example we use built-in audio signal provided by MATLAB. The handle.mat file is loaded which contains an audio signal is sampling frequency. The signal represents the original clean audio. After that, random Gaussian noise is generated and added to the original audio signal. This type simulation a real-world situation where signals are often affected by noise. The noise signal is created by combine the original audio with the generated noise. Next, the band filter is designed using a Hann windows. A bandpass filter allows frequency within a spectral range to pass through, with the intention frequency below and above that range. In this code, the lowest cut-off frequency is set to 100 Hz and the upper cut frequency set to 1000 Hz. This means the only frequency between 200 and 2000 Hz are prevalent. The cut-off frequency are then normalized, then anchored frequency, which is the half of the sampling frequency. This normalized type is required when design digital filter in MATLAB. The code then play three video signal: the original video, the audio signal, and the filter video. This allow us to clear here that effect of the noise, how the band pass filter improve the signal quality. Finally, the waveform, the original noise and filter signal are plotted. By comparing this plot, we can observe how the noise effect and the signal and how the band pass filter smooth and clean the waveform. In conclusion, this experience shows that Hann windows bass and bandpass filter effect in reduce noise while the preventing import frequency component, making it suitable for practice audio and signal processing application.
What is ECG? ECG stands for electrocardiogram. This is a medical test used to measure the electrical activity of heart over time. It is widely used to diagnose heart conditions such as arrhythmias or irregular heartbeat. The ECG signal typically contains periodic waveforms that represent the heart electric impulse, which must be accurately captured and analyzed. The problem in ECG signals are often contaminated by noise such as 1. Baseline wind, low frequency noise caused by breathing or body movement. 2. Power line interference, high frequency noise from electrical system. This noise occurs critical feature in the ECG signal like a P wave, QRS complex, and T wave. Let's talk about summary. Windows techniques are important in digital signal because they affect how accurate signals are analyzed. The rectangular windows offer high-frequency solution, making it useful for detect small signal changes, and its simple construction allow efficient real-time processing. However, its sharp edge can introduce noise. The Hann window reduces this problem by smooth the signal edge, which the lower noise and improve signal clarity. This makes it costly useful for applications such as ECG signal processing, where clean and reliable signals are required. Overall, the rectangular windows is an important and practical tool in ECG signal processing. In conclusion, both of the rectangular and Hann window have their own strength in digital signal. The rectangular windows is easy to implement and suitable for simple application, but it can cause unwanted noise due to spectral leaking. The Hann window provides smooth translation and better noise reduction, although its slightly reduced frequency resolution. MATLAB simulation show that Hann window perform better in application require accuracy and noise suppression. Therefore, the choice of window depends on the application need. The rectangular windows is appropriate for basic tasks, while the Hann window is more suitable for more previous and noise sensitivity application.